This video is about normal subgroups. Our main task is to form new groups using cosets. So we start with a group G and a subgroup H, and we're going to consider the left cosets of H and G, and we want to form a group from those left cosets. So the group we form is going to have a name. It's called a quotient group. To form a group, we need a binary operation. So we take two left cosets of H, say AH and BH, and we combine them really in about the only way we know how, and that's to multiply the representatives AB together and look at the left coset of H that we form by multiplying on the left by the group element AB. So things seem to be going well, right? The identity in this group would be just H itself, which we can write as EH. And to see that, if we take EH times, any other left coset AH, we multiply the representatives to get E times A times H. But E times A is just A. And so the coset H serves to preserve the left coset AH. And it's the same as if we were to multiply on the right, same situation. Okay, well, we have an identity. What about inverses? So if we have a coset or a left coset AH, then the natural inverse for that would be A inverse times H. And further, the operation is associative, right? You can see in this chain of equations that everything ultimately boils down to the fact that the associativity property holds in the group capital G. So all of this looks very, very good, and it seems that we have solved the problem of making a group out of cosets, and we can go on and amuse ourselves with other topics. But there's a problem in what we've just done. So on the previous slide, we defined what we thought was a binary operation on left cosets and showed, in fact, that that operation, if it is in fact binary, gives rise to a group that can be formed with these left cosets. However, apparently there's a problem, and to illustrate what the problem is, we're going to do this example where our group capital G is the symmetric group, and the subgroup H is the group of order 2 generated by little g. Now, if you look at the left cosets of H in capital G, you can compute that you get this list right here. And in fact, the only three sort of distinct left cosets are this one H itself, which consists of E and G, FH, which is F and FG, and F squared H, which is F squared and F squared G. We know that we have gotten all of them because their union together, their disjoint union, is actually equal to all of the group. So now let's consider the binary operation that we defined, or at least the so-called binary operation that we defined on the previous slide. So let's take two left cosets, say FH and FH, and we're going to multiply them together using that operation. So that gives us, just by multiplying the representatives, F squared H, which is this set consisting of F squared and F squared G. On the other hand, we can also take FGH, which is a perfectly good left coset of H, and multiply it by itself. To do that, we multiply the representatives together. That is, we take FG times FG. But FG is of order 2, and so FG squared is equal to E. And so the result is just H itself, consisting of the elements E, G. So I submit to you that there's a problem here, an issue that needs to be resolved. And perhaps at this point you'll want to pause the video and see if you can detect the issue for yourself. Okay, so now perhaps you have been away and thinking about what the problem is here. Notice that the coset FH is equal to the coset FGH, right? You just go up to the list here and notice that these cosets, they are exactly the same set. And so that needs to imply, you know, if this operation star on cosets is legit, that is, if it's some binary operation, then it's got to be well defined as a function. That means that when we take FH times FH, we would need that to be equal to FGH times FGH. But this doesn't happen, right? Notice that FGH is one thing, or FGH times itself is one thing, whereas FH times itself is another thing. So this equation, which we need to hold, does not hold. So we'll have to figure out how to address that problem. In the last example, the problem may have been that we weren't using the right type of subgroup. And that begs the question of, well, what is the right type of subgroup to use if we want to form a group out of the left cosets? And it turns out that the right type of subgroup, or the correct type of subgroup, is what's called a normal subgroup. So a subgroup capital H of a group G is said to be normal if little g times little h times little g inverse lies again in capital H for every little h in capital H and every little g in capital G. So what's that really saying to us? Well, if you hand me any element of capital H, say this little h, then I should be able to conjugate it by anything in the larger group and wind up again back within H. So here we have two examples illustrating the idea of a normal subgroup. And the first example should look familiar because it's the same example that we had on the previous slide. So here the larger group is the symmetric group S3, and the subgroup, again, is the two-element subgroup generated by little g. Right, and we want to know whether this subgroup is normal, and we fully expect that it will not be normal because of the failure that occurred on the previous slide. But anyway, let's see. So let's start with an element in capital H, and let's then pick an element in the larger group. I don't know, let's say F, and we're going to conjugate the element of H by the element of capital G. So that means that we're going to multiply F, G, F inverse. But remember that F inverse is F squared. And also remember that GF squared is the same as FG. And so the end result of this conjugation gives us F squared G. And now what I want to do is look back and see whether that lives within H. And it does not live in H. So I took my element in H, I conjugated it by something in the group, and I wound up with something that was not in H. And that means that H is not normal. in G. Well, maybe we'll have better luck with our second example. So here we have a new subgroup. Again, the larger group, G, capital G, is the symmetric group S3. But this time we're going to look at the subgroup K, which is generated by the 3-cycle F. Well, let's compute a conjugate or two and see what happens. So now let's just pick, say, F in K, and we'll pick something in the larger group. I don't know, like say G is in the larger group, S3. And we're going to conjugate F by G. So we're going to take G, F, G inverse. And we'll remember that G is its own inverse. And we also remember that FG is the same as GF squared. And since G is its own inverse, G squared is the identity, and so that means that we wind up with F squared. And now I raise my head and I check to see whether that result lies again within K, and in fact it does. And this is not a fluke. It turns out that if you conjugate anything in K by anything within the larger group, you will wind up again within the subgroup K. So all the other possible conjugates, and we're not checking this here, I'm just telling you this, all the other possible conjugates also lie in K, and that tells us that K is a normal subgroup. So some notation for this, I think I'll just point it out right here. Whenever you have a normal subgroup, you use this triangle symbol to indicate that it's a normal subgroup. So how, aside from the definition of a normal subgroup, can we tell that a subgroup is normal? That question is answered by this theorem. So if we have a subgroup H of a group G, the following are equivalent. So first, H is normal. The second is that the conjugate of the set H by any element in the group G yields the set H again. And the third is that the left coset of H by little g is the same as the right coset of H by little g. Now, just to remind you, when we say that the following are equivalent, what that means is that the truth of one statement implies the truth of the others. And if one of the statements is false, then all the statements are false. Okay, now there are a number of implications that we would need to prove in order to prove this theorem. Here we're just going to prove that statement 1 implies statement 3. So we're going to suppose that H is normal. And we want to show that the left coset GH is equal to the right coset HG. So we're going to pick an element, say G and little h, inside of this left coset. Then that element, G little h, I can rewrite that as GH, G inverse times G. But because H is normal, capital H is normal, this conjugate right here has to sit again within H. So let's call it, say, H tilde, right? So that thing there is a member of H. And this product then is in the right coset of capital H by little g. So therefore, the left coset GH is contained within the right coset HG. And in a similar way, the right coset is contained within the left coset. So the two sets must be equal. Now let's return to the problem of forming a group out of the left cosets of some subgroup. So this time we're going to be successful. So we have a theorem that says that if you start with any group, capital G, and a normal subgroup, H, then the collection of left cosets of H does indeed form a group under the operation we discussed previously. Namely, you take two left cosets and multiply them together essentially by multiplying the representatives A times B and using that product to form a new coset, a new left coset of H. Okay, now you might recall early on that we showed that if this operation is well defined, then there's an identity and it's associative and there are inverses. So everything is in place except that we need to show that this operation is well defined. So let's do that now. So let's suppose we've got cosets AH and BH that are really equal cosets, and the same with CH and DH. The issue is, in order for this to be well defined, we need A times C times H to be equal to BDH. If that holds, then this operation will be well defined. Okay, so that's what we're to prove. Now, A is a member of the left coset AH, but that's the same as BH, and so I know that I can write A as B times something in H. And similarly, I can write C as D times something else in H. So now let's just pick some arbitrary thing, K, inside of the left coset AC capital H. And our goal ultimately will be to show that that thing lies also in BD capital H. So anyway, if little k is in AC capital H, then k can be written as A times C times some little h, where little h is in capital H. And that's going to lead to this chain of equations. So we already know that k is AC times little h. But remember, A and C we have been able to express as BH1 and DH2, respectively. So we make those substitutions. And now I'm going to insert a D times D inverse in front of the H1. And that doesn't change anything because D times D inverse is just the identity. But what it does do is it introduces a conjugate of H1, namely D inverse H1D. And because H is normal, that means that that conjugate is some other element, H3, that lies in capital H. Now, what you might notice here is that we have a product of a bunch of things that lie in H. And because H is a subgroup, that product, again, has to lie in H. And therefore, this K, this little k that we started with, is written as B times D times something else in H. In other words, K lies in the left coset, BD times capital H. And that allows us to conclude this subset relationship here. And a very similar argument will give you the opposite opposite inclusion, and therefore the two cosets are equal, and that's what we wanted to show. Now, this new group that we're forming using the left cosets of H, as we said, it's called a quotient group, and it's denoted cleverly, I guess, by this quotient, G slash H. In the next two slides, we do examples of quotient groups. So in this example, our group is the integers under addition, of course. And our subgroup is just the cyclic subgroup generated by the element 3. So this is just going to consist of multiples of 3 within the integers. So the first thing we need to check in order to make sure that the quotient group makes sense is whether the subgroup H is normal in G. So if G is an integer and H is an element of this, group of multiples of 3, then when we take GHG inverse, that in additive notation is G plus H plus minus G. But remember, the integers are abelian. And so we can move this stuff around any way we want. So that's G plus minus G plus H. But that's, of course, just H, which does, again, lie in this subgroup H, capital H. And so this means that capital H is normal. Okay, the moral of this story is that if you start with any abelian group and look at any subgroup within that abelian group, then that subgroup is going to be normal. And so the quotient groups will always make sense when the larger group is abelian, because all of the subgroups are going to be normal. Okay, well, what are the left cosets of H? Well, we've got H itself, which essentially is just all of these multiples of 3. And then what could we do? Well, we could take 1 plus H. So that takes everything in H and adds 1 to it. We could take 2 plus H. And that's all the multiples of 3 plus 2. And now we could keep going, but there's no reason to keep going, right? Because if you take all of these 3 together, these 3 sets, they partition the integers. H is the set of all integers that leave a remainder of 0 upon division by 3. 1 plus H is all the things that leave a remainder of 1 upon division by 3, and 2 plus H is all the stuff that leaves a remainder of 2 upon division by 3. And that is everything in the integers. So our quotient group, in this case, G, what we call G mod H, consists of 3 objects. So let's put them together in a table. In fact, because it consists of 3 objects and 3 is prime, we know that this is going to be a cyclic group, so it should look a lot like Z3. but let's make a table. So when we take H and we combine it with H, remember that consists of adding the representatives. And so we wind up with H again. In fact, we could call this 0 plus H, right? Maybe it's a good idea to do that here. Okay, now 0 plus H together with 1 plus H, that gives us, according to our operation on cosets, 0 plus 1 plus H, which is just 1 plus H. And that goes here, and likewise here, and similarly here, and here. Remember that the coset H itself is the identity in our quotient group. You might remember that from one of the very early slides. Okay, now let's compute 1 plus H together with 2 plus H. So we'll denote our operation on cosets by addition here. It seems to make sense. And how do we do that? Well, remember, we add the representatives. So this is going to be 3 plus H. But 3 plus H gives the same thing as H. And so this will be H. And likewise, this will be H. And you can continue to fill out the table. Okay, so that is the group table for G mod H, the quotient group of G by H. And it looks like just Z3. Right, in fact, if you were to just wipe out all of the H's from this picture in this table, you would wind up exactly with the operation table for Z3. So in this next example, we go back to our favorite group, the symmetric group on 3 letters, S3. And this time our subgroup H is going to be this the group of order 3 generated by F. Now remember, a few slides ago we showed that this subgroup is normal in G, and so the quotient group does make sense. So what are the cosets? Well, we have H, which is EF and F squared. And then the next natural thing to do is look at GH, which would be G F squared G and FG. And notice that if we take those two together, we get all of S3. And so we're done with the left cosets. And therefore, this group, this quotient group, is going to be just this group with 2 elements. So it should be a lot like Z2 and its table, which I guess we could write as EH and GH. And EH is the identity, so we just get H, GH, and GH there. And really the only thing to do is to compute GH starred with GH. And remember how the operation works, that we're supposed to just take the representatives G times G, take that result, and use that to form a left coset of H. But G times G is the identity. So that's just H. And there's our lovely group table, and it certainly looks a lot like Z2. So we finish this video with a couple of quick facts about normal subgroups. So first of all, any subgroup of the center of a group is going to be normal in the group. And that means that if G is abelian, then any subgroup of G is normal, as we discussed a couple of slides ago. The second theorem says that if the index of H in G is equal to 2, then H is normal in G. So what this means is that H has half the size of G. So whenever H is half the size of G, just like on the previous slide, H will be normal in G. So just a quick discussion about these theorems here. So for theorem 1, let's suppose we have a subgroup H that's contained in the center of our group G. And let's suppose we have an element H in capital H. And let's compute a conjugate, GH, G inverse, where G is in the larger group capital G. Now, we want this conjugate to lie again back in capital H. But H is in the center, H is contained in the center of the group, and that means that this little h commutes with everything, including this little g. And so I can write this as H times G inverse, which is equal to H, which is in capital H again, right? And so that implies that, that H is normal. Because if we take the conjugate of anything in capital H, we wind up again with something in capital H. Okay, now for theorem 2, remember that the left cosets and the right cosets of any subgroup partition the group. So we can write G as, H union G times H, where here G is some element that's not in H. That's all that matters, okay? And this union is disjoint, right? So remember, there are only two cosets. That's what this index here means, is that there are only two cosets. And so G is written as a union of those two cosets. It's a disjoint union. And the same thing is true for right cosets. Okay? Now, what this tells us is that GH is equal to HG. That is, every left coset is equal to the corresponding right coset. Now, we had a theorem a few slides ago that said whenever you had a situation like this, when the left cosets are exactly equal to the right cosets, then that meant that H is normal.